Gracias, Santi. Hola a todos. Estoy haciendo un postdoc en Bilbao, en la UPV, y trabajo con Ricardo. Y como me falta un poco de vocabulario en ciencia, voy a hablar en inglés. So this work is about doing meteorology above lakes on Titan. And to do that, I did modeling, and I worked in collaboration with two people in the US, Scott Ruffin and Alessandro Soto, in Boulder and the Southwest Research Institute. And also our student, Enoa, helped a lot on this work. When we see Titan from above, we see like an homogeneous orange ball. But in fact, if we look in specific wavelengths, we can see that it's not homogeneous at all. There are a lot of things at the surface, which are quite nice. So for instance, the big orange thing that we see here at the equator are dunes made of organic sand. And in the dunes, there are also a lot of things. And in particular, we have pictures of riverbeds and round rocks that proves that some liquid is flowing at the surface of Titan. And also we have directly images of lakes at the poles. So, and this liquid, well, it's really cold on Titan, minus 180 degrees Celsius. So it's not water, it's methane. And so we have lakes, rivers, but also we can see clouds made of methane that can be quite big. And also we have proofs of rain with the humidification of the surface. So we have a complete cycle, methane cycle on Titan. So from the evaporation of lake to the formation of clouds, rain, and rivers. And so we, and there are a lot of lakes at the poles of Titan. So six seas or lakes that are really big with 1,200 to 200 kilometers long, and 45 that are a bit smaller but still quite big. And so we think that this evaporation of these big reservoirs will impact strongly the methane abundance in the atmosphere of Titan. So we want to know how much is evaporated. And also we think that the local weather above the lakes will strongly influence this evaporation of the lakes. So to understand that, we decided to build a model. So our two collaborators in the US started to, created this model a few years ago. So they started really simple with just in 2D with a lake of methane surrounded by land. And they looked with simple physics and they looked at what was going on. And so they saw that as the here is not saturated with methane, so we have evaporation of methane above the lake. And during evaporation, the lake cools down and cools down the atmosphere just above, which becomes denser than the here above the land, and which creates a circulation, so at the surface from the lake to the land, and then closing, doing a loop like that. And doing that, they saw that the energy fluxes at stake were really small, a few watts per meter square, so it's super small, and it's the order of magnitude of the insolation at the surface of Titan, even though the rays have to go through the thick atmosphere. So when I arrived, I added the solar and infrared fluxes to this model because we think it could have an impact. And in fact, yes. So we see the same sea breeze, but now there is a diurnal variation of the sea breeze. So as we can see here, so let's start with the left plot. So it's the horizontal wind. So in red, it's toward the right, blue toward the left. And here we have, it's half a lake. So the lake is the 25 first kilometers. And so we see that we have this circulation of sea breeze, so the wind going from the lake to the land at the surface and the reverse in altitude. And we see that the extent of this sea breeze changes with the time of the day. So it extends during the night, and during the day when it's turbulent, it diffuses everywhere and starts again. And on the right, we have the vertical wind. So just to see that it closes the circulation. So we have a subsidence above the lake, and then wind going up at the front of the sea breeze. So these are for the 2D models, but then we said, oh, let's go to 3D because maybe it will be quite different. So here are the first 3D results we had. So it's just a round lake seen from above, and here we have the horizontal wind. So we clearly see the wind going from the lake to the land. So we still have this sea breeze, and we can also have a look at the vertical wind. So we still see the wind going down above the lake and up at the sea breeze front. But 3D simulations are more computationally expensive because it's in 3D, so we should have good reasons to do that. And the first one was that, well, in 3D we have this round lake view from above, but in 2D, well, the 3D equivalent is a lake infinitely long along the other dimension, so a long rectangular lake, and it's quite different. So we expect to have differences in the wind due to divergence, convergence effects. And in fact, that's what we see. So here's again a plot with altitude of the horizontal wind. So here it's what we have in 3D. So we still see this sea breeze around the lake, which is at the center here. And what we had before in 2D is on the right. So we see that the sea breeze is less extended. And this is because of a convergence effect due to 3D, just simple as that. And so when we see this effect also in the vertical wind, and this time we see that due to convergence effect in altitude above the lake, we have a stronger subsidence above the lake and a fainter vertical wind at the front of the sea breeze. So small differences, and so we have to go to 3D then and do long computations. And what is fun by being in 3D too, it's like we can simulate real lakes with real shapes. So this is an example of Feya Lake on Titan. And so we see that the sea breeze follows the shape of the lake as expected. So this is the wind at the surface. And well, we saw a nice, interesting thing is that if we look a little bit in altitude at 200 meters, above a round lake, well, there is no wind, but above the strange-shaped lake, we see the formation of currents above peninsulas. So it's a new thing we have seen with these 3D models. And looking at the vertical wind this time, so above a round lake, we had the homogeneous subsidence above the lake, but above this strange-shaped lake, we see some small plumes and irregularities really locally. What we had been able to do also is to simulate different a group of lakes, because on Titan there are locations with a lot of lakes at the same place. And so here, for instance, it's a simulation during the day, so with the vertical wind and the horizontal wind. And we see that in this case, each lake has its own sea breeze cell, and they don't interact with each other, just interfering at the border. And for the horizontal wind, we see like a big peninsula winds also. But during the night, it's quite different because the sea breeze is more extended. And so finally, all the breezes merge and form a big one. And inside this big cell, we have completely crazy winds, like going from external lakes to the central lake, and then from the central lake over the land to the land far away. And so it was unexpected from 2D simulations, and it's good to have 3D simulations to do that. And so we could investigate a lot of lakes, or wheel-shaped lakes on Titan, and especially here I went to, well, a small round one to the biggest lake we have on Titan. And we see that the wind is bigger with bigger lakes. So we can get a maximum of the wind we can have on the lakes, which is really small, in fact, but on Titan, everything is small. It's 0.1 meter per second. And so this is not enough to trigger form waves on the lakes. And this is consistent with what we see on radar results. So no waves in normal conditions. But, well, in really specific places with strange topography or during storms, maybe we could form, but we have to do other simulations to be sure. So also, I'll talk about at the beginning about evaporation and everything. So here is the methane mixing ratio evaporated by the lakes. And so we see that on bigger lakes, we can reach at some places really high humidity, 95%. And so we can think that in specific conditions with topography or other things, we could reach the saturation and form fog above the lakes at some places. We did, well, it's really recent, in fact, is that on Titan, lakes are usually surrounded by high topography terrains, like what we see on this radar profile. It's 300 meters high walls on the side of the lakes. So this could have a strong influence on the winds. So we recently added this topography on the model. So this is the results of the comparison of the previous simulations with the topography on the left and on the right with the topography. And so we see that it does not stop the sea breeze, which has to go above the topography and down on the other side. And we have like strange stuff like stronger winds on the slope wind on the external side of the topography. And at the end, the sea breeze goes less far, but it changes a little bit things. And now we are investigating the effect on the evaporation of the lake. And a last quick thing, if you did not have time to go to Enora's poster yet, go, you still have one break to do that, because she studied the case of really specific small lakes that are surrounded by strange terrains with different properties. And so she investigated the effect of these different properties of the surface on the sea breeze structure. So I'm done, thanks.
¿Alguna pregunta? ¿Qué efecto, which effect can this have over a mission like dragonfly, for example?
Thanks for the question. So dragonfly will be at the equator, and so it cannot go to the lakes, which are far away. But at the equator, it will go to a crater. So with the same topography as I showed just above. But there will not be a lake inside the topography, but there could be moist terrains that could trigger evaporation too, and small sea breezes also. So it's our next step is to remove the lake, but put moist terrain instead, and to try to simulate what winds could see dragonfly. And it's really important because it will fly from place to place. So it's nice to have a good idea of the winds. For now, we have small winds, so it's okay, but it's better to check everything. Especially as dragonfly would be at the equator, so the influence of the insolation would be stronger, and so maybe it could trigger stronger winds.
Okay.
So next steps.
Thank you. Any more questions? Okay.
Hi, thanks for the talk. I'm just curious about what composition of your fluid that you're considering you're using for the winds, and if you're including cases or particles suspended, and if that can alter the winds.
Okay, thanks. So in fact, it's really the hazes on Titan are much above, like in the few last kilometer above the surface, it's quite clear. So the hazes should not have an effect in the simulation box, but we take it into account for the infrared flux that comes from above.
Hi, Audrey. Thank you. Very nice talk. How difficult could be to change from methane lakes to nitrogen lakes?
Thanks. So in fact, lakes are not pure methane lakes. Now, there is also ethane and nitrogen dissolved in it, in them. And so it's like we have the idea to one day improve the description of the lake, add some other stuff, also add currents, because for now the lakes are still and do not move, but in fact the differential temperature could induce currents. So to add something else, well, we have to do some work, but we could simulate, well, we did it before. We can simulate it by saying that the humidity above the lake is higher, and so it will do the same thing as if we added a little bit of ethane into the lake, because it will decrease the evaporation efficiency. So we did a little bit of tests like that. So in fact, if there is something else in the lake, the evaporation will be less efficient and we will have less sea breeze.
Hi, I have a simple question. This is very nice work and very convincing. This is a very advanced model and there are so many detailed predictions. So I was wondering if it is very close to the surface, so it's difficult to validate this data with measurements, no? So are you proposing particular measurements that could be done in the future, maybe, to validate these predictions?
Oh, can you repeat, because there was another sound. For no. Okay, thanks. So we cannot go and see and measure the wind, but with the provision of fog that I said, so we have some one American collaborator which is working on Cassini data, and who is finding some places where there are fogs seen over the lakes on Titan. So if we can reproduce the formation of these fogs, like that could be quite of a validation first step.